Well, welcome back from our break. I hope that you had an enjoyable break and that you were able to talk to people that you haven't seen in a while, and that you also met some new people, shared thoughts and ideas, and again, met new people. Our next keynote speaker is widely known as one of the inventors of the internet. Dr. Vinton G. Cerf is Vice President and Chief Internet Evangelist for Google, where he continues the global policy development and the continued spread of the internet. He co-designed the TCP/IP protocols and the architecture for the internet. He has served in executive positions at MCI, the Corporation for National Research Initiatives, and the Defense Advanced Research Projects Agency, and he's on the faculty of Stanford University. In December 1994, People magazine named Dr. Cerf as one of that year's 25 most intriguing people. He is the recipient of numerous awards, including the U.S. Presidential Medal of Freedom, the U.S. National Medal of Technology, and the A.M. Turing Award. President Obama appointed him to the National Science Board in 2012. Ladies and gentlemen, it is my pleasure to welcome Dr. Vinton G. Cerf.
Well, good morning, everyone. I have a terrible cold, so two things are going to happen. One, I'm not shaking hands with anybody. And second, I may run out of time before we can do Q&A. And even if we did Q&A, I might not be able to hear you because I just landed from the West Coast, and you know what happens when your ears are stuffed up, et cetera. So you're going to have to just put up with me. I'm the bad news guy, and I'm hoping there's some good news people who follow me or who preceded me, but I'm the bad news guy is telling you we're losing this battle. What's the battle? Well, to begin with, we want and don't have safety, privacy, and security in cyberspace. We don't have that. Those responsibilities do not lie only with the manufacturers of equipment and the programmers and the like, but they lie with you and me. There are policy issues. There are performance and behavior issues, including the general public. Users have a key role here, and I'm not trying to make a pun out of that. They have to exercise practices that produce better quality, security, and safety, and privacy. People who pick bad passwords are examples of people who are not doing their job. I mean, do you have any idea how many people use password as their password because it's so easy to remember? But of course, the bad guys know that too. So we'll come to other kinds of notions that we might try to introduce into this cyberspace to make things better. There's also an issue about liability. I used to make my living writing software. My first job out of school was at IBM. And I think over the past 50 years or so that programmers have gotten away with murder because when they make mistakes, they say, well, it was just a bug, regardless of how much damage it might have caused. At some point, somebody's going to figure this out. Now, you've heard about cyber insurance. That does not solve anything. All that does is perhaps help you with the financial consequences of a screw-up. But what it doesn't do is fix the bugs. So we're going to start with trying to understand where those bugs come from and what we can do about it. By the way, this is not just an internet problem. Some of you will remember diskettes, 5¼ floppies, 3½ floppies. You remember running around, you know, in your sneakers, trading diskettes around. They had viruses in them too. And so this is not a new problem in the cyberspace world, but it preceded the internet. But internet exacerbates the problem. It allows us to propagate malware very rapidly and very broadly all over the place. The fundamental reason that we have this problem is we have really bad programming tools. We don't have software that helps us identify mistakes that we make. Simple things like buffer overflows or off-by-one bugs. What I want is a piece of software that's watching what I'm doing while I'm programming. Imagine it's sitting on my shoulder and I'm typing away. And it says, you just created a buffer overflow in line 123. What do you mean I have a buffer overflow? It says, look at the damn text. I want something that will actually watch what I'm doing. I don't think this is entirely impossible. There are a number of programming languages and other mechanisms that are being introduced that should help a little bit. TLA+, for example, Or there's something called COQ, C-O-Q, which is a programming language that lets you express your intent. Any of you who remember trying to prove software correctness will recall that this didn't work out very well. And the simple reason for this is that most programs you can't express the intent of most programs in first-order predicate calculus. They're too rich. I mean, what if it's a financial program or a stock trading program or a video game? There isn't a simple expression that says this program is doing what it was intended to do. But at the very least, we can write programming environments that track the program's intent, its flow of control, and maybe you can make assertions about the software and have this support program validate your assertion, or maybe say, no, I cannot validate that, and that will help you avoid stupid mistakes, which most bugs tend to be. So that's my beginning peroration here. There's another thing which we have only begun to reintroduce into our landscape, and that's hardware reinforced security. We do a lot with software to try to detect and reject various kinds of malware or other kinds of inappropriate access. But hardware can help us here. Way back when, in the 1960s, MIT was involved in a project called MAC, which is multi-access computing. This was the early days of time sharing. They modified Honeywell GE 635 to become a 645, and the differences were twofold. One was virtual memory, which allowed you to expand the apparent memory of the machine and run concurrently a much larger set of programs than otherwise would be possible. But the second thing they did was to put in 8 hardware rings of protection. That is to say that you had to be in a particular ring in the machine in order to execute certain privileged instructions. And the most privileged instructions were down at ring 0. And so what would happen is if you executed one of those privileged instructions, you would be trapped down to a kernel in the program that said, who the hell are you and why do you think you can execute this instruction? And if you couldn't show to that piece of software that you had the authority to do that, then that program was terminated. So this was a hardware reinforced mechanism which allowed us to essentially help the software protect from mistakes that would otherwise be damaging. The x86 chipsets actually have these rings of protection in them, but nobody is bothering to program using that hardware mechanism, at least not that I am aware of. There's also an interesting thing that was developed at NSA during the Enduring Security Framework development, and that was the notion of assigned bootstrap. When the machine first boots up, there's a piece of code that's pretty vital because that's the thing that pulls in the operating system. And the idea here was to put in a hardware checksum, a hardware assigned hash of the bootstrap. And if the hardware couldn't validate the hash of that bootstrap, it would not boot up. And this was to avoid somebody putting in a new bootstrap that pulled in the wrong operating system. That kind of hardware mechanism is, in fact, quite powerful and quite protective at the very earliest stages of booting up the machines. There's also notions of trusted computing bases. I'm sure most of you have heard of those. And I would argue that we need them. We need pieces of hardware that can lock up crypto variables, that can perform cryptographic functions in the hardware and not allow any of that to escape into the rest of the system. These kinds of things can protect the machine against various kinds of invasion. Everyone here, I hope, is familiar with two-factor authentication. I'm a big proponent of that. In addition to a username and password, you want to have a device, at least, that will generate yet another cryptographic password, which is modified each time you use it, so that even if somebody sees that or is able to capture it, it doesn't do them any good. They can't reuse it for some really big cycle. At Google, for example, we are required to carry a small dongle with us that generates a cryptographic password on demand. We have to put that in order to protect ourselves. So even when we're inside our own system, inside our own network, we're not allowed to get access to Google resources without having that second factor available. Another thing that we do at Google, and I imagine many of you do as well, is monitor systems continuously. We have a vast array of computers in multiple data centers scattered around the world. We are monitoring at all levels of activity, down at the hardware level, and all the way up to application space. The idea behind continuous monitoring is twofold. The first one is to establish baseline, what's normal. In a system as large as ours, something's always broken. And so the real question is not, is everything perfect, but rather, is it broken in the average amount that we would expect on a system of this scale? When we now have a baseline, then we can see ourselves departing from that baseline. We know when we've sent out, page 404, page not found, or 500, can't access this file. We know when we've done that. We monitor that, and if our rate of rejection or rate of error goes beyond some average amount, then we can flag that as an anomaly and call in the troops and make sure that we tried to do something to fix the problem. More often than not, it's a piece of software that we propagated that had a bug in it, and it had an impact on the operation of the system, and we have to scramble to pull that update back and replace it with something else. We need more of this kind of thinking in the systems that we use. Cloud computing is another example. It's really a reincarnation of the old idea of factory computing. Some of you may remember textbooks that showed what people thought time-sharing computers were going to be like in the future. There's this giant building with some steam coming out the top with a huge computer in it, mirroring the giant mainframes of the 1960s. Well, today we have warehouses full of computers, but there are billions of them, or at least millions anyway, of chips, and with cores, and then multiple cores, 64 cores, 128 cores, that are executing all in parallel. So it's a huge parallel time-sharing environment that we're in. So we've just reinvented the historical time-sharing system, except on a scale bigger than anything anybody ever contemplated. What's nice about this cloud environment is that it's relatively uniform, so that when we make any changes at all, they propagate throughout the entire system all at the same time. You don't have to wait for somebody to decide to update a piece of software. Now, on the flip side of that, when you propagate a new code load and it has a bug in it, it propagates everywhere and it pollutes everything. So we do very careful propagation. We have the very small numbers of machines that are running new software, and we test against that. We're back to this consistent distribution of data as well. We replicate all the data across the data centers. So if you're using any of the, like Google Docs, for example, or Gmail or something else, we literally make copies of everything that you're doing, and we spread it not only within a data center, but across data centers. So we have this giant backbone network, optical fiber network, which is pushing data back and forth around the data center. So even if we lose a whole data center, we still retain the data. And so that's a continuous background operation. It's actually really hard to do that in real time. If you ever use Google Docs with more than one person using the Google Doc, you can simultaneously both be editing the document, and that information propagates in all the copies in real time. There's something else that we do at Google, and that's called DIRT. It's a sort of disaster recovery test. We go on the backup systems live. We shut off access to our primary personnel. We run in backup for a week in the live system. And that takes real guts to do that. But it's the best way we've ever found to making sure that our backup systems actually work. I bet a lot of you are very comfortable. Maybe you're backing up your own personal computers who have an external drive, and you do this religiously. Have you ever tried to reload from the backup? Because if you don't, the day that you need that backup, you may discover nothing was actually being written on the disk. And so you have to swallow hard and do the backup and make sure that you're getting what you're looking for. So we do that, and I'm very proud of Google and its operations team for doing that. There's more detail about this DIRT exercise that's in the URL that you should be able to see there. And by the way, I'm assuming that the slides will be available. There's nothing secret here, so they're free for anyone who wishes to get copies if there has been an arrangement for that. So I've been thinking about the civilian population. I mean, here we are. We're mostly worried about the military, but you know what? The military is using an awful lot of civilian gear these days. But let's talk about what the world is like for the civilians out there. We have fire departments. When a house is on fire, you call the fire department. When your computer is on cyber fire, we don't have any place to go. And I've been wondering, maybe the private sector, especially small, medium-sized businesses, ought to have a cyber fire department to call whenever something appears to have gone wrong. They're under denial of service attack, their malware is propagating through the system, other bad things are happening. This is a very appealing metaphor, but there are some little problems. When your house is on fire, it's okay for your neighbor to call the fire department and tell them your neighbor's house is on fire, please put out the fire. And the fire department shows up and they break the ceiling, they break the windows, and they pour water in and they make a big mess. But they put the fire out because we recognize that a residential fire is a hazard to the rest of the community. But now let's imagine that Company A is a competitor of Company B, and Company A calls the fire department and says, Company B is on cyber fire. So the cyber fire department shows up, shuts down operations for 2 or 3 days, so they're trying to figure out what the problem is. Meanwhile, Company A is sitting here running perfectly well, making money. So it's clear that we have to be very careful about these kind of metaphors. We'd have to figure out exactly what are the rules, who can call the cyber fire department to help put out a fire. Maybe it's only the company that thinks it's on fire. So those are, these are worthy metaphors to think about, but as I say, they're never perfect. What about security? I don't know about you, but I've always found that there's a certain amount of inconvenience associated with good security. And I've wondered, almost academically, is there some irreducible amount of inconvenience that accompanies good security? I think our purpose will be to shrink that down to the minimum possible, consistent with maintaining good quality security. But if it's too inconvenient, people won't do it. For example, if you tell people, you must change your password every 6 weeks, and it has to be some long mishmash of 24 characters, including funny symbols and things like that. If you have enough accounts, you're not going to be able to remember any of that. So what are you going to do? Well, you're going to write them down on a piece of paper, post it on your laptop, or you're going to have an unencrypted file sitting in your computer with all that. I have 300 passwords that I have to deal with, and I have an encrypted file sitting on my computer. I wish that I had a two-factor authentication system that could allow multiple identifiers to be on the same key, in the same crypto device, because I don't want to carry 300 dongles around with me and then try to figure out which one is the right one to plug in. So we have to think a little bit here about scaling in order to make this stuff work. Now, some people will say, well, what about single sign-on? Doesn't that sound really cool? All of your passwords are over here, and you invoke that thing, and it picks out the right one and does this for you, until somebody discovers that there is this place that has everybody's passwords. That's a really great target to go after. So I'm not a big fan of putting all my passwords in somebody else's mailbox. I would much prefer to have the ability to carry one device which has many hundreds of keys in it, and let the system figure out which is the right one to use. There's another issue here, and it has to do with international hacking that's going on. We all are familiar with, especially the Russians and the Chinese. The question in my mind is whether we should consider doing the same thing that we did after the 1962 missile crisis, establishing a hotline. Before we start a nuclear war, we should have the opportunity to talk. Excuse me, we think this bad thing is happening. We are about to launch a nuclear attack, but maybe we should talk about it first. Well, if you think you're under cyber attack from somebody, and if you have an opportunity or an option to respond, the response may be in the cyberspace, or the response might actually be a more kinetic response. But before we do anything, having a discussion about that with the putative target might be very important. First problem is false flag attacks, where we go after the wrong party. So accreditation is, or attribution rather, is exactly an important thing to do. The second thing is that in that conversation, it very well may be that we can resolve the problem and step down the tension. But I don't know whether we have such a thing. I think there have been some discussions at high levels about the possibility of establishing these cyber hotlines. I'm in favor of that because it doesn't commit you to anything other than talking, and there's nothing wrong with that. The other thing that I thought might be interesting is that for you to know what the original security model was for the internet. Some people run around saying there wasn't any and that we ignored it, and I feel compelled to defend myself about that. It is true, it is absolutely true that we didn't have a lot of cryptographic mechanism in either the ARPANET or in the subsequent internet, with one exception. In the ARPANET case, we had something called a private line interface, which was a full-up KG34 end-to-end crypto that allowed us to do classified stuff across the otherwise open ARPANET. When I was doing the internet design around 1975 or so, we began implementation of the protocols that had been developed in 1974, and I went to NSA and said, I think we should talk about how to secure this thing. And so NSA participated in the detailed evolution of the TCP protocols. There are certain things in those protocols that reflected some of their ideas. We also designed and built something called BCR, which stood for Black Crypto Red. It was all about packetized crypto. Think about this. Most of the crypto up until that time was line-based stuff, continuous cryptography. And what do you do when you have a packet switch system where the packets don't necessarily arrive in the same order that they were encrypted? So you have to be able to decrypt things out of order. Well, we had to develop the technology for doing packetized encryption and decryption, which we did. Eventually, one of the products that came out of that was called Blacker. So we developed this method with NSA's help. We tested it initially using DES because that was an unclassified algorithm. For actual use in military, of course, we used KG equipment that was classified. The problem is that the architecture and details of that system, some of which was classified, I couldn't share with a lot of the people who were actually doing the internet development. So and there's another little problem. Everybody knows what public key crypto is, but back around 1975 or so, it didn't exist. And I was in the middle. I was at DARPA in '76, and we were pushing very hard to get the cycle of design work done. We were going through 4 iterations of TCP. And in 1976, Whit Diffie and Marty Hellman at Stanford University published a paper on new concepts for cryptography, including public key crypto, but they didn't provide any algorithms. They just provided a concept. The RSA algorithm didn't show up until a couple of years later, and by 1978, I was freezing the design of the internet because I wanted to get the damn thing built so we could see if it would work. So we didn't include public key crypto at that point. However, you all know it has been added since that time. There are lots of other things that we could do with the internet to increase its safety and security. They are things that you can introduce into the architecture and strengthen it. We don't have to start all over again necessarily. We can use some of the technologies that are available to us to retrofit the systems that we currently use. So I wanted to acknowledge a debt to NSA for their help in the very early stages of internet design and the introduction of packetized cryptography. Well, now there's another worry for you, and that's called the Internet of Things, sometimes called cyber physical systems. I'm very worried about this because there are purported to be many billions of such devices on their way. There are certainly millions, if not hundreds of millions of them by now. All of you probably are familiar with a recent problem with some webcams that were taken over by some botnet herder, the Mirai Virus. 500,000 webcams that had no control, no access control at all, or had well-known username and passwords. The botnet herder had no trouble assembling 500,000 of these and then aiming a 1 megabit per second stream per camera times 500,000 to the Dyn Corporation, which was the target. That's about 500 gigabits per second of traffic. That's more than most anybody can stand. Eventually, we moved that system over to Google to try to shield them because of our capacity. The big problem here, of course, is that it was easy to assemble that Mirai virus, and it overwhelmed Dyn. And to make matters worse, Dyn happened to be the company that was also serving domain name service for a number of companies, and so there were cascading damage effects as a result of that denial of service attack. It's just unacceptable to allow people to release into the private sector, or in fact into military procurement, devices that have not had adequate consideration of security. I think it's just unacceptable. In fact, there's legislation that's been introduced by Senator Warner speaking to government acquisition of these types of devices, saying that they had to meet certain criteria of safety and security before they could be purchased, and I think that's a good idea. But I want to tell you a couple of other big problems that you will face as individuals. Eventually, you're going to accumulate a collection of these devices, and they will seem very attractive on the surface. They do things for you that you don't have to do for yourself. They're autonomous pieces of software. but they are made by multiple manufacturers, and the manufacturers are not necessarily coordinating on commonality, common identification, authentication, cryptography, and the like. Imagine just the configuration problem. You have 100 devices in your house, maybe about 200, and you move to another house that has another 200 devices. The last thing you want to do is spend the week typing IPv6 addresses into some configuration program to get all this stuff to work right. What about updating software? I already ranted about bugs in the software. There are going to be bugs in the future. How do you make sure you can update these devices with software that makes them more secure? How does the device know whether the update is coming from a legitimate source? How can it tell whether it didn't get modified on the way? Does it have integrity? This is all back to cryptos and crypto hash, digital signatures, strong authentication, and the like. There are also some fairly big privacy issues here. Even if it's just temperature sensing, I do this every 6 minutes or every 5 minutes. The temperature sensors in every room in my house record the temperature and send it through a mesh radio network to a server in the basement. I know, only a geek would do that. But the whole idea here was to have information about how well my heating and ventilation and air conditioning work for the course of the year. If somebody gets access to the temperature data over a 6-month period, they may be able to figure how many people live in the house, what are your diurnal patterns, when are you likely not at home. If you want to rob the house, this is good information to have. So even something as simple as the temperature data might turn out to be hazardous and therefore needs to be protected. There's also this notion of ephemeral access. Let me take the medical example. You're in a foreign city, never been there before, you suddenly have a medical emergency, you're in the emergency room. Probably the last thing on your mind is hiding all of your medical information from the people who you were hoping will save you. So you want them to have access to everything. However, when the crisis is over, assuming you survive, you don't want them to have continued access to all of your medical information. So we need to have this ephemeral ability to grant and revoke access to private information or classified information. So we have to figure out how to do that. The credit card people sort of do that by having expiration dates on the credit cards after which you have to get a new card. So this notion of ephemerality is not new, but it's something we need to consider in the design of these systems. I alluded to strong authentication, and I could not overemphasize this. I do not want devices in my house, my home, my car, on my person that are not fully access controlled. I want the device to reject any attempt to control by an unauthorized party. I want the device to reject passing any information to an unauthorized party. I want to have the ability to control that. And of course, it gets a little complicated. Imagine you have a fully automated home and you invite some guests over. How do you introduce the guests to your house? And what is it that the house has to know about the guests to allow the guests to turn the lights off and flush the toilet? I mean, we need to figure out exactly how complicated is this going to get. And then when they leave, you have to undo all of that to make sure that they don't have control when they shouldn't. And then it gets more complicated with adults and the kids aren't supposed to have as much control as the adults do, except if I look at today's world, the kids have a better ability to mess around with this stuff than the parents do, so that may turn out to be a conundrum. But all of this stuff is going to require really clever design to make it habitable. Otherwise, we're just going to turn off all of the access controls and things will go down the drain. There. Okay, so here are the things that still worry me in the little bit of time that we have left. We get very detailed security practice recommendations from places like NIST. And I feel qualified to criticize here because I still report to NIST as a special government employee, specifically to the group that produces these documents. And they do a good job of giving us advice. However, what's missing is the ability to measure how well the device was followed and how well the security actually succeeded. And we need to figure out how to measure that in very concrete terms so we can assess how well we are in fact implementing secured systems and not simply checking a box saying I followed all the rules. So that's hard, by the way. Figuring out how to measure the security and safety of a system is difficult. In the software world, where you're trying to figure out whether software is resistant to random input, there's a process called fuzzing, where you just throw all kinds of kamikaze packets at your software and see whether it falls over or not, or how well does it detect and reject. these things. You can imagine a similar kind of security fuzzing activity where you launch all kinds of attacks against the software and to see how well it resists. That's one possibility, although I would really love to have a more refined way of testing the quality of my security implementation than simply throwing stuff at it and hoping that something sticks. I do have to make one other admission here, and that is that every time I make a bad mistake, it's usually because I made an assumption that was wrong. And even though I keep learning this lesson over and over and over again, I still make assumptions, and I still get in trouble. And so my bottom line here is take nothing for granted, make no assumptions, assume that everything is on the table, you are at risk in every dimension when you're doing system design in particular. And I do want to add one other thing in the few seconds I have left. I think I actually have one other slide. There it is. Well, the first line is obvious. Every one of you sitting here knows that, or you wouldn't be here. The second thing is that the private sector really does need better tools and incentives to build security into their system. And whether that is liability or better tools, better teaching, better training, whatever it is, we have to provide the private sector with a reason to supply you with better security and better safety and better privacy. I mentioned that cyber insurance doesn't fix the vulnerabilities. It just gives you a little bit of extra cash to recover from a serious blunder. And finally, I think we have to think seriously about liability and consequences for bad practices. There must be a price to pay for doing a bad job. And I'll leave you with that, and I thank you very much for your time. Virtual handshake. Oh, you want me to go back up again?
Thank you very much.
Oh, thank you.
Dr. Cerf, thank you so much for coming out. And we know you're under the weather, but thank you for coming out and speaking to us.